So suppose x is congruent to A mod n, where n is composite. We can rewrite this as a system of congruences where the moduli are pairwise coprime. But the system depends on how we factor n. So what's the best way to break n into factors? So remember, concrete doesn't hurt. Suppose we want to rewrite x congruent to 11 mod 30. Since 30 is 2 times 3 times 5, we could use 2, 3, and 5 as our moduli. And so we have x congruent to 11 mod 2, which reduces to 1 mod 2, and x congruent to 11 mod 3, which reduces to 2 mod 3, and x is congruent to 11 mod 5, which reduces to 1 mod 5. But we could also factor 30 as 2 times 15, since again, here we have the greatest common divisor of our moduli as 1, and we have x congruent to 11 mod 2, which reduces down to 1 mod 2, and x congruent to 11 mod 15. Or we could use the factorization 5 times 6, and so 11 mod 5 becomes 1 mod 5, and 11 mod 6 becomes 5 mod 6. Or 30 is 3 times 10, and so 11 mod 3 becomes 2 mod 3, 11 mod 10 becomes 1 mod 10. And so there's a number of different ways we could do this, but remember, working mod n allows you to work with the numbers from 0 to n minus 1. Since using the individual prime factors reduces the congruence the most, we might find it easiest to use 2, 3, and 5 as the moduli. Now be careful, don't solve one problem. What if we have something like mod 360? In this case, the prime factorization of 360 is 2 cubed times 3 squared times 5, and in order for the moduli to be coprime, all powers of a prime have to be in the same modulus. And this suggests that we should use the moduli 2 cubed 8, 3 squared 9, and 5, which gives us Now consider simultaneous congruences where the moduli are not coprime, like we can break each modulus into a product of prime powers. Now we already did that for 360 and we got, since 84 is 2 squared times 3 times 7, we get, and this gives us a system of 6 congruences, but the moduli still aren't coprime. Since the new moduli are powers of a single prime, the only non-coprime moduli will consist of different powers of the same prime. But since x congruent to A mod PQ means x congruent to A mod P, we can start with the highest power and work our way down. So x congruent to 1 mod 8 also gives us x congruent to 1 mod 4 and x congruent to 1 mod 2. And note that if x is congruent to 1 mod 8, then x congruent to 1 mod 4, this other congruence, is automatically satisfied, so it's redundant. Likewise, x congruent to 8 mod 9 also gives us x congruent to 8 mod 3, which we can reduce to 2 mod 3. So if x is congruent to 8 mod 9, then x is congruent to 2 mod 3 automatically, and we don't need to worry about this congruence either. And so our original system of congruences becomes a new system of congruences where the moduli are coprime. And since the moduli are coprime, there is a solution, which will be, and we find that 1097 does in fact solve both congruences. This gives us an approach to solving the Chinese remainder problem if the moduli are not relatively coprime. We could rewrite each congruence as x congruent to something where the moduli are prime powers that are factors of the original moduli, and rewrite each congruence of a prime power as a congruence of equal or lower prime powers. And if at any point we obtain contradictory congruences, the problem is unsolvable. Otherwise, we can use the Chinese remainder theorem and find a solution to the system of congruences. So let's take a system of congruences like this. 24 is 2 cubed times 3, so x congruent to 7 becomes Since 54 is 2 times 3 cubed, we can rewrite this as a system of congruences mod 2 and 3 cubed. And finally, since 25 is a prime power, we'll leave this congruence in its original form, and this gives us a system of congruences. Now, since 8 is a power of 2, we also need to consider what that congruence is for lower powers of 2, and so that will be, and note that this includes our other congruences, so we don't need that other congruence. We also have x congruent to 11 mod a power of 3, so we can rewrite this in terms of lower powers of 3. But notice this is inconsistent with one of our other congruences, so this problem is unsolvable. What if we have something like this? Working as before, we get and again, our power of 2 induces some other congruences, and our power of 3 induces some other congruences. But this time our congruences are consistent, and so this system is solvable. And in fact, we find the solution, which we can reduce mod the product of the moduli, which gives us, as our least positive solution, and going back to the original problem, we find, and so we have a solution. Now, we can always rewrite any system of congruences as a system of congruences with pairwise coprime moduli. If the resulting system is consistent, we can always find a solution to the new system of congruences. By the Chinese remainder theorem, the solution will be unique mod the product of the new congruences. But will it solve the original system of congruences? Let's take a look at that next.